Dear students, now we discuss how we find residue of a complex function. First, what is residue? Before starting residue, we come to Lorentz series expansion. And the Lorentz series expansion of fz about point z equals to a is fz equals to sigma n equals to 0 to infinite a n z minus a to power n plus sigma n equals to 1 to infinity bn by z minus a to the power n. This expression contains positive powers and here are the negative powers. If we put n equals to 0, we get a naught, n equals to 1, a1 z minus 1 plus n equals to 2, we get a2 z minus 2 square plus up to and so on. And if we put n equals to 1 and second term, we get b1 upon z minus a plus b2 by z minus a whole square plus up to and so on. Where an equals to 1 upon 2 pi I integral c fz upon z minus a to the power n plus 1 dz, and bn equals to 1 upon 2 pi I integral c fz by z minus a to the power minus n plus 1. The coefficient b1 of 1 upon z minus a in this expression in Lorentz series expansion of fz is called residue of fz at z equals to a. If we find b1, put n equals to 1 in bn, we get 1 upon 2 pi iota integral c fz upon z minus a to the power minus 1 plus 1. This becomes 0. It means 1 upon 2 pi I integral c fz dz. b1 is the residue. It means residue at z equals to a is a coefficient of 1 upon z minus a. How we find residue? First, residue at a simple pole. If fz has a simple pole at z equals to a, then residue at z equals to a equals to limit z tends to a z minus a fz. Next, residue at a pole z equals to a of order n. If fz has a pole of order n at z equals to a, then residue at z equals to a equals to 1 upon n minus 1 factorial dn minus 1 by dz n minus 1 z minus a whole power n fz and whole value at z equals to a. And third, this is general method. Residue at a pole z equals to a either of order n or simple pole. It is general method. Residue at z equals to a equals to a coefficient of 1 by t, where t equals to z minus a. I take a column, determine the poles and the residue at each pole of the function fz equals to z square upon z minus 1 whole square z plus 2. First we find poles. Poles are obtained by putting denominator 0. It means z minus 1 whole square z plus 2 equals to 0. We get z equals to 1 1 minus 2. It means fz has a simple pole at z equals to minus 2 and z equals to 1. We get two values. It means z equals to 1 is a second order pole. Now, residue of fz at z equals to minus 2 at simple pole, limit z tends to minus 2 z minus minus 2 fz. We get limit z tends to minus 2 z plus 2 and fz value z square upon z minus 1 whole square z plus 2. Z plus 2 cancel out and put z equals to minus 2 here. We get minus 2 whole square by minus 2 minus 1 whole square, that's 4 by 9. Next, residue of fz at double pole z equals to 1. Earlier we take formula of order n, put n equals to 2 here, we get 1 upon 2 minus 1 factorial, 1 by 2 minus 1 factorial, d by dz, z minus 1 whole square fz at z equals to 1. 1 by factorial 1, d by dz, z minus 1 square, z square upon z minus 1 square, z plus 2, z minus 1 square cancel out. Now, d by dz, z square by z plus 2 at z equals to 1. Differentiating by quotient rule, denominator as it is, differentiation of numerator minus numerator z square and its differentiation 1. Now put z equals to 1 in this expression. 1 plus 2 into 2 minus 1 by 1 plus 2 whole square. We get 5 by 9. This is the value of residue at double pole. Okay.